Good morning, good afternoon, good evening, good maybe late evening, wherever you are. And I'll be talking today. I'm Lubos Mitash from North Carolina State University, and together with Gani, we'll be talking about pseudopotentials, as you heard, or effective core potentials. And as I always used to say, this is the most difficult subject, even maybe in quantum Monte Carlo, because it's very technical. All the constructions or methodologies which are used are complicated. Actually, I tried to look back into the history. It turns out that the pseudopotentials are 70 years old at this point. So as you can imagine, a lot of knowledge is accumulated on this topic. And very often this is the most complicated part of the code. Actually, that's true both for quantum Monte Carlo, but also for DFT codes. And on the other hand, it's a typical example of effective Hamiltonian, which is a method which is used very much in physics, where you want to eliminate the degrees of freedom which are off by either scale or energy window. And therefore, in some sense, it follows the systematic work of physicists in constructing effective Hamiltonians. From practical point of view, they save phenomenal amount of hours of computer time, as you will see, and they simply allow to push the science further than you could do without them. And in fact, sometimes you are pushing even the limits of the possibility. There are actually cases where they are unavoidable in some sense. Otherwise, you have just too big of a burden of an inefficiency. Okay, let's outline what we'll be talking about today. So I'll very briefly mention one particle self-consistent methods where the pseudopotentials were born so that we understand the origin. Then talk about the key point of core versus valence partitioning. We'll talk about length and energy scales and dependence on atomic numbers Z. Then we'll put down the effective core potentials and division into core and valence. Then we'll look on the impact of this partitioning on total energies and fluctuations and efficiency gains. And then we'll a little bit talk about how this is really done in the code. Of course, this can't be completely explained in one talk, but nevertheless, at least the flavors of two main methods, how they are treated. And then Gani will continue with, how the actual things have been derived. What is the new generation of these objects, which we developed also here at NC State, and forms and examples and practical use as much as possible as you can do it within half an hour. Okay, so let's first remind us, all of us, I'm sure that you know this, a density functional theory, which is a one particle self-consistent method where you simply get the total energy from a function of the density, and density you built from one particle eigenstates. And that the construction requires one particle effective potential, which is constructed in DFT as a complicated function of the one particle density. And there is a self-consistent loop. You get the orbitals from there, you calculate the density, feed into the effective potential, and so on until you reach the self-consistency. Conceptually, it is similar with the zero-order approximation for the wave function method, which is Hartree-Fock, where you minimize the total energy for a given ansatz of a Slater determinant of one particle orbitals. And again, we end up with one particle equation with effective potential, with the difference that in this case it is constructed from orbitals, not from the density. As such, it has some non-local properties, so in some sense it is a more complicated method, but conceptually at this self-consistent loop level, they are very similar. The point is the effective potential, and we'll see how they get actually modified later. Okay, now Why we talk about effective cores and valence states? Because there is a good reason for that. Atom simply covers a number of scales, both in energy and in spatial distribution. Maybe first, let's talk about the spatial distribution. So this is the amplitude of the wave function of the one particle orbitals for the carbon atom as a function of the distance from the nucleus. And here you see, so that's R times psi s. Okay, so that's the amplitude. If you square it, it's the probability density on that one particle state. And so you see here the following. There are essentially kind of three regions. One is very close to the nucleus, when one state is the maximum very close to the nucleus, and it tails goes down exponentially quickly. And then we have the valence states 2s and 2p, which sort of have some amplitudes in the core region, but their tails go way out. And in particular, for us, it's very important, the bonding region. Note the very important point. If you would take a square of these, the core state would be exponentially damped very strongly in the bonding region. Therefore, you see that there's sort of a natural division of the space into the core region, which is given in this case maybe a little bit beyond 1 atomic unit in the distance, and then the rest. If we take a more complicated atom like a copper, here we have sort of one regime more. So we have the core states like 1s, 2s, but then there is a state which is 3s and 3p, which is sort of mostly in the core, but the tail kind of goes uncomfortably far, and it actually probes a little bit the bonding region. The bonding region is then, of course, in the place where the 4s electron is dominant, but also a very significant part of the 3D goes there, and it actually goes beyond the bonding region. So D state is kind of strange. It has a significant presence both in the core, but it goes through the whole valence, and the tail is actually long. So in this case, we see that actually this 3s state is kind of difficult to dismiss a priori. And in fact, we'll see that we'll need to include them into the valence space later. Okay, if we look at what happens in the molecule where the orbitals hybridize, so you see the core states remain core. There's not too much going on in the valence space. Actually, the density here is relatively small, so that you see where the atom has the sort of the edge and the end of the core. But then the valence states are, of course, going all over the molecule, and obviously they are everywhere. They are a little bit in the core, but otherwise they are all in the valence space. They, of course, form the bonds. They change very significantly, while the core states do not change essentially at all. Now, even more important point for us is the following. The eigenvalues of the one particle eigenvalues of the core states have span incredible range of scales if you go through the periodic table, because they scale as the atomic number squared divided by number of the order 1, especially for 1s, 2s, and so on. So they go from, say, 100 to about 1 million electron volts. Now, semicore states are somewhere in between. They are between roughly 30 and 100 electron volts. Again, uncomfortably close to the valence window of energies, which is going from, say, 10 to the minus 3 electron volts to about 30 electron volts. Okay, so why I'm mentioning and emphasizing the energy aspect? Because of the following reason. We know that the statistical methods, of course, always depends on a crucial point in the method, which is the variance. And variance is determined by the largest scale which is present in the sampling. And in this case, it would be, the energy coming from the core electrons, which will be then scaling as z to the 4th power, which is a pretty steep growth if you think about going through the periodic table. So efficiency of the sampling of the valence properties, which are outside of the cores, such bond energies, gaps, and so on, weak bonding, van der Waals bonding, and so on, is actually extremely low. In fact, if you think about the atom which doesn't have nominally core, like a helium, the sigma square typically is of the order of 0.2, but for the copper, it is about 100. So there is a slowdown by a factor of 500 going from, an atom which doesn't have a core to an atom which has a sort of a medium-sized core. And for even heavier atoms, it's so impractical that it becomes actually possible. It doesn't make too much of a sense to work with the cores, with systems with the uranium, because simply all the sampling effort will be spent on sampling the core fluctuations, which are irrelevant for most of the valence properties. Therefore, we basically come to the logical conclusion that we have to do something about the cores and actually abandon them in one way or another, but in such a way that the valence distribution is not disturbed too much, or it is disturbed minimally in such a way that it actually, whatever we construct as an effective Hamiltonian, will mimic the presence of the core and will tune the valence states right to be there exactly like if the core electrons were present. So we'll represent the core by an effective operator, and we immediately understand that it cannot be a simple potential because there is a different number of electrons in the core in the different angular momentum channels, S, P, D, and so on. Therefore, this at the minimal level, this has to be atomic angular momentum dependent. So it will have these projection operators on spherical harmonics, which are the eigenstates of the one particle atomic angular momentum operator. And then there will be a local potential, which sort of tunes the whole thing into the right energy and spatial distribution. Now, you might have heard pseudopotentials, which is the term which is used mostly in condensate matter physics, or in quantum chemistry, they are called effective core potentials. And simply, this is the form which I repeat from the previous view graph here. Now, the VL are the radial pseudopotentials functions for a given L symmetry channel. Local potential is essentially that mimics the long-range thing, which is then Z effective, namely original atomic numbers minus the number of nucleons, minus the number of electrons which were omitted from the valence space. And these are the projection operators. And here is some maximum number of occupied channels, namely the number of non-local projection operators. Okay, so what is the non-locality? Let's recall the one particle effective equation for the DFT or Hartree-Fock. So in some sense, here is the external potential in this red ellipse, which would be nominally minus Z over R. But in the case of pseudopotentials, it is replaced by these, for S channel, there would be VS potential plus V local. For P channel, there would be VP plus V local, and so on and so forth. So you see that the effective potential depends on the channel. Therefore, we say this is non-local. Obviously, the non-locality will demonstrate itself that the matrix element of this non-local potential will have off-diagonal matrix elements. And that's a big complication for for quantum Monte Carlo. For the variational method, it's a complication mostly technical. It is still complicated, as you can see. So the action of the operator on a wave function which in our case will be probably a complicated object. Namely, it will not be a sum of products of one particle orbitals, but it will not be separable if there is a J-star factor or more complicated constructions. Therefore, this action, actually this integral, has to be evaluated numerically. And what does it mean? Well, we need to do an integral over the spherical harmonics, which means integrate over the spherical surface integral. And for that purpose, we use special quadratures. Code does that for you, but it's good to remember that you have a number of quadrature points, and it essentially evaluates it anywhere where the non-local potential reaches. So this is essentially technical, still complicated, but nevertheless it can be done. Now, what do we gain here? And that's an important point actually to look at. And I have chosen the iron atom, which is both deep core, semi-core states, and of course the valence. And now you see here these three columns where there are total energy in Hartree-Fock, VMC, fluctuations, efficiency, which is the inverse of the fluctuations time, the decorrelation time, and the valence systematic errors, which you incur using effective Hamiltonian instead of the original Coulomb Hamiltonian. And now you see that nominally all electron is 0. I put that into the quotes because of the note which will follow. But let's now focus on these two other columns. You see that with the argon core, namely having only D and S, 3D and 4s electrons, you end up with a pretty good speed up over, the efficiency gain is almost four orders of magnitude. But the point is that the errors are also growing, and suddenly you end up with systematic shifts for some quantities up to about half an electron volt, which we deem not to be acceptable. Now, if you look at taking the semi-core, namely 3s and 3p electrons into the valence space and adjusting correspondingly the effective core potentials, then you end up with a pretty good speed up, about one factor of 100, and you end up with errors which are controllable. They are below 1/10 of an electron volt, which for many purposes is enough. Now, let's talk about the 0 in quotes. There's an important point. If you do a straightforward calculation of the iron atom with the nuclear potential of in all electron setting, there are scalar relativistic effects which actually affect the differences by roughly 0.2 electron volts or so. Therefore, you are not very accurate with all electrons. You have to put in scalar relativistic effects. And those are very easy to fold into the effective core potentials. So actually, with effective core potentials, many of the differences in the valence space will be more accurate with ECPs than using non-relativistic all electrons. Okay, now comes the difficult part. What to do with the non-local operators in diffusion Monte Carlo? As I said, non-locality means that off-diagonal matrix elements are present. What does it mean, non-diagonal matrix element in the operator in the diffusion Monte Carlo? It means non-local jumps in the propagation of the Walkers in the position space. Namely, you move an electron from one point to another. The complication is that here it could be around half of the atom. It is not a tiny displacement as is dictated by the time step, because simply the non-local matrix element implies instant moves in the space, which could be about, around the whole atom, going several atomic units. That, of course, very easily could violate the fixed node condition, which I'm sure you already know at this point. And therefore, we have to do something with this non-locality. One version how to deal with this is to use the localization approximation, where you replace the original W operator, which is the genuine, ECP guy or pseudopotential guy, and you replace it by this projected version. You apply it on your best trial wave function which you have, and you divide by the trial function. So in some sense, you build effective operator in the Schrödinger equation, and it is now localized. It's a many-body beast, which is very complicated, but you don't care because you can calculate it numerically. Now, this is a complicated subject, what happens, but basically there are two main points. The bias which you create by this localization approximation is quadratic in the trial wave function error. Therefore, it converges very quickly. We know one basic rule in quantum Monte Carlo. Unless your trial wave function is really very good, it doesn't make sense to start even the calculation. Simply, the fluctuations will be large, and biases from lousy constructions will show up. Therefore, it doesn't make any sense to invest the computational time into. Therefore, you work very hard on the trial wave function. Once you work very hard on the trial wave function, you diminish also this bias. And in fact, the bias is not very large. In fact, in differences, it is typically smaller than is the fixed node bias. On the positive side, the method has a zero variance property. As you are converging with the trial wave function into the exact, the variance which is coming from this term is actually going to zero quadratically fast. There is an alternative to the localization approximation, and that is called a T-moves method. And this has an important point that it restores the upper bound property. If you simply introduce sort of a localized effective core potential into the Schrödinger equation, you create sort of an unknown operator. You know it actually only numerically, and therefore the energy is not necessarily an upper bound in the localization approximation. In T-moves, you eliminate this problem. You buy a little bit of a problem elsewhere, but that can be handled with. And so how it is done with the T-moves? Basically, T-moves does the following. You do a non-local move if it doesn't change the sign of the wave function. Namely, it doesn't violate the fixed node condition. And of course, there you can estimate from these products of the matrix elements of the ECP operator and these trial functions at the original and the attempted move. It is either positive or it is negative. If it changes the sign, you do not sample, but you wait by the localization approximation. And therefore, you take the best from the both worlds, namely you sample when it doesn't harm you, and you localize when it does harm you. The important point is that the total energy is an upper bound in this construction, but there is no zero variance because you are making moves with the potential, which is complicated, and there are instant moves in the position space, and therefore that generates a little bit of a variance. There is some increase in computational effort, but it's not fundamental. And therefore, these two approximations have sort of a complementary properties. One has a zero variance, but doesn't have an upper bound. T-moves have upper bound, but no zero variance. So in some sense, they can be used interchangeably. But the T-moves, if you are interested in being really on the side of the variational energy, total energy, then the T-moves are actually way to go. It has also some additional advantages in stabilizing the calculations. They might be more complicated to stabilize under particular conditions, with the localization approximation. Okay, so let's recapitulate what we talked about it. So if you use these effective core potentials or pseudopotentials, you gain a huge amount, especially for the heavy atom, on the fluctuations and efficiency. It goes 2 orders to 3 orders, 4 orders of magnitude if you talk about the, say, 5D elements you are maybe even beyond the 4 orders of magnitude speed up. Practical point is also that the wave function requires smaller and much smoother bases. In particular, you know that pseudopotentials for plane waves are crucial. Basically, you can't do too much with the plane waves without those. It reduces the number of degrees of freedom. Scalar relativity is included, which is a big advantage. So up to 4Ds, you are safe with the relativity. At the 4Ds, it starts to sort of creep in through a spin orbit, but even that has a natural extension in the ECP construction. So it is actually straightforward to generalize that to spin orbit. Cody Melton will talk about it next week. There's nothing additional. I think that I'm more or less within the time. And of course, I'll be happy to respond to the questions or comments.
Thanks very much, Lubos. We'll give people a moment to type any questions that they might have. Okay, I see there's already one from Roman Fanta. Why is it essential to have for QMC a non-divergent effective core potential at the origin?
Basically, then you end up with the regions of configurations, which has a very large fluctuations in the energy. And in fact, it will dictate the efficiency of the whole calculation by this region. Simply the largest energy scale, which is in the calculation, dictates efficiency of the whole method, although you are interested in something else. You would have to smooth it out. For example, it is trivial to smooth out the Coulomb potential. You take 10⁻³ atomic units, where you replace the divergence with something like a well-tuned constant or a smooth function. This is trivial to do. In fact, for very heavy elements, you actually use a form of the nuclear potential which doesn't diverge, but has a finite density, because there's a nucleon which has a finite density. So in calculation of uranium or those elements, you actually use a potential which doesn't diverge. It will still be terrible to use actually in QMC, because the fluctuations will be giant. And therefore you want to remove the scale which is damaging your efficiency so much that you slow down by 4 orders of magnitude. Actually, you want to go in the direction of an effective Hamiltonian and controlling the bias which you generate by the effective object. If you can control that bias, everything is okay.
Thanks, Lubos. So I don't see any other questions yet, but I do have one of my own. And people have asked about this in some of the previous weeks. And as you explained, in quantum Monte Carlo, and also actually quantum chemistry, we use the semi-local form of effective core potentials. So one projector per angular momentum channel, in effect. And in at least density functional theory, at least with plane waves, you can see where this is going, we are much more commonly using multiple projector potentials. So Vanderbilt's, Blockle's, or Don Hammond's schemes. And at least in DFT, the claim is that this leads to improved transferability and accuracy. So is this relevant for quantum Monte Carlo and also quantum chemistry? Should we be worried about using the single projector semi-local scheme, for example?
That is a very interesting point. Of course, it gets into technicalities even deeper, but let me give a short, I'll try a short answer. Semi-local forms are typically used in quantum chemistry. In some sense, almost nobody in quantum chemistry uses these more complicated constructions, because they simply are more or less used to this construction and don't even think about going beyond. In condensate matter physics, the Hamiltonians got more complicated, and you get these multiple projectors and things like that. What we see is in our new generations of ECPs, as Gani will present, it is possible to tune the accuracy with semi-local form to the accuracy of more complicated construction. That seems not to be the limiting case in almost every aspect which we have tried. Now, there is a different point why they are actually this construction, more complicated construction with multiple projection or Kleinman, Bylander, those types of things are used in condensate matter. Because you can get that operator into a product form, which tremendously improves the efficiency of the DFT methods, especially with the plane waves. Therefore, there you gain at least 2 orders of magnitude if it is in the Kleinman-Bylander form or multiple projection form. And therefore, there is a tendency, and actually simplifies the code tremendously and speeds up those codes tremendously to use them. Now, Gani will mention that we have transformation of the semi-local into the Kleinman-Bylander forms. Therefore, you could use them in the effective, in this form in usual codes. But in QMC, more efficiency is the least non-local it is, as it is on the semi-local form, the better, because there you have less numerical orbitals to numerical integrations to do.
Thanks. Yeah, apologies for the technical question, but it had
this is good at least to talk about it, although we'll not do it justice here in one answer, I guess.
Well, I do see one important question, and then we'll switch over to Gani. So this question is from Adam Denchfield. Do the same pseudopotentials have to be used for the QMC and the DFT that generates a trial wave function?
Yes, it is. Since we are talking about the converging towards the exact wave function for a given Hamiltonian, we want to have the Hamiltonian systematically the same through the whole process. Namely, in the process of generating orbitals, then in VMC, DMC, and everything. So we are really looking at the ground state energy of a given effective Hamiltonian. We claim that we can always improve the effective Hamiltonian, for example, including more electrons into the valence space from the core, improving the ECPs. But after that point, we say this is the Hamiltonian, we want its eigenstate. Therefore, you keep the same thing as going through.
Thank you. Let's now switch over to Gani's part of the presentation. So you need to stop screen sharing, Lubos. Yes.
Yes.
Okay. Can you hear me and can you see the screen?
Thanks for checking, Gani. Yes, we can hear you and we can also see the screen. Go right ahead.
Perfect. So my name is Gani Anaberdiev. I'm from North Carolina State University in the group of Dr. Lubos Mitash. So I'll be talking about optimization of pseudopotentials. So just to give an introduction, as we've talked in the previous weeks, DMC is a very accurate many-body method, and it can estimate very accurate correlation energies. So to give an example, if you take silicon in diamond structure, and if you use single reference, fixed node DMC can actually recover roughly 99% of the correlation energy. However, for DMC to be able to make reliable predictions, it has to be solving the accurate Hamiltonian, which is represented by the effective core potentials in this case. So in that sense, an accurate relativistic pseudopotential, or ECP, is highly desired with some of these properties. First is that it has to be constructed in a many-body way. So the ECP must reference the correlated relativistic all-electron data, and the ECP itself has to be optimized using an accurate many-body method. Also, we want it to be tested, and it has to be preferably universal so that it can be used in any method, such as mean field DFT or Hartree Fock or QMC, or other many-body methods such as coupled cluster, which is similar to the spirit of using the same Hamiltonian as in the all-electron case. So the Hamiltonian itself must be the same throughout for all of that calculations, and has to be universal. So I'll give briefly an overview of how ECPs were optimized conventionally and historically. Essentially, one would take a subset of atomic spectrum S and generate a relativistic all-electron reference state using some mean fields, say Hartree-Fock. And using that data, one can do two optimization routines. One is the so-called energy consistency of the atomic spectrum. And as the name suggests, essentially you try to match the gaps of ECP spectrum. So here, this would be the gap from the ground state, and you would need to minimize the difference between these two. And this is essentially the objective function that we're trying to minimize when we're optimizing the ECP. Another related method is the so-called shape consistency, where it primarily uses the quantities of single particle orbitals. So in this case, we would have the single particle electron eigenvalues. You would match the ECP versus the electron eigenvalue. But then we'll have quantities such as, for a chosen cutoff radius, we'll have quantities such as the value of the orbital at that cutoff radius, the derivative of that orbital at that radius, and this so-called norm, which is given by this integral here. And essentially, you would try to minimize this quantity here, which would give you the optimized ECP. Okay, so now I want to introduce this so-called correlation consistent effective core potential. So this is a newer generation of ECPs, and essentially it goes beyond mean field approaches such as Hartree-Fock, and it tries to incorporate explicit electron-electron correlations. And so here the reference data is again scalar relativistic, but it's a fully correlated data which correlates all the electrons, namely core valence and valence electron correlations using an accurate method such as coupled cluster with singles, doubles, and perturbative triples. And the objective function itself is related to many-body quantities. As you can see, this is similar to the energy consistency in the previous slide, but instead of Hartree-Fock gaps, one uses the coupled cluster gaps. And then small contribution from the norm is also added so that we don't overfit this quantity over here. And ideally, one would want a simple parameterized form with few Gaussians so that it's easy to use in a variety of codes. And one desires that these are highly transferable so that they need to be tested, especially on, say, hydride or oxide molecules with variety of bond lengths, especially with a heavy focus on compressed bond lengths. So here I'm showing some results. Here so if you look at the figure on the right here, this is the mean absolute deviations of 3D transitional metals for a variety of core approximations. So these are all core approximations where the reference data is an all electron with coupled cluster, all electrons are correlated, and the mean absolute deviation is defined as such for a set of chosen states. So here the BFD is Burkhardsky, Filippi-Dolk, Dirac-Hartree-Fock ECPs, which were designed for QMC. SDU is the Stuttgart group, again Dirac-Hartree-Fock ECPs. ECEPP is the newer trail needs ECPs, which did consider the correlations in constructing the ECPs. CCECP is this so-called correlation consistent ECPs, also a new generation correlation consistent ECPs, considering also the correlations using coupled cluster. This UC is an all electron calculation, as you can see here on the red, but it does not correlate the corresponding core using in the coupled cluster calculation. So all of those electrons are frozen and they're not excited essentially. So as you can see, if you look at the graph here, some of the ECPs have really large errors in the maths, but this reddish purplish color is the CCECP, and it shows that there's a significant improvement over older generations. And in fact, if you notice that it's actually below the uncorrelated core for most of these cases. So we can see that there's one can do a significant improvement using the same ECP form. and we can obtain such an improvement over older generation of ECPs. Here's another example. This is 4s and 4p elements. Here we're showing actually two quantities. One is the MADs, and the other is LMAD, which stands for low-lying state MADs. So essentially only when considering the low-lying excitations. And the whole MAD represents the whole spectrum, which includes electron affinity, all ionization potentials down to the core, neutral excitations, and etc. And as you can see here, the CCECP is represented by the green color, in both in the MAD, which is shown by the solid lines, and in the LMAD, which is shown by the dashed lines. There's a good improvement over the older ECPs. So this actually shows that because we're optimizing this in the atomic spectrum, this actually shows that we have optimized it better in the training data. But how does this carry to more complicated systems such as molecules, or say even more complicated systems such as solids? And in the following slides, I'll focus on the molecules, and I'll show that the transferability of these molecules are improved for hydrides and oxides. So first, let's look at the hydrides. So here, these are the essentially vanadium hydride molecule and bromine hydride molecule. So this tests essentially the quality of sigma type bonds. And if we look at the left figure here, essentially what we're showing here is the discrepancy of variety of core approximations with respect to high accuracy, relativistic, coupled cluster, all electron data. And this is the binding energy discrepancy from that all electron data across variety of bond lengths. So the closer it is to zero, the better. And as you can see, also the chemical accuracy here is also shown in this gray region. So that's roughly 0.043 EVs. And as you can see, some of the ECPs tend to either underbind or overbind, and the CCECP is very close to zero and with minimal errors. Similar thing could be seen in the bromine hydride. Some of the older ECPs shows this overbinding. Here, the uncorrelated core actually underbinds significantly near the compressed bond lengths. And the CCECP is throughout the whole bond lengths, it's within the chemical accuracy. I forgot to mention here, this dashed line represents the equilibrium geometry of the molecule, and this left side is the bond length in the left side here is close to dissociation limit of the molecule. So it is essentially probed until the molecule dissociates. So let's move to the oxides here. So this would be probing the quality of pi bonds. So these graphs are similar to the previous graphs. So essentially similar discrepancy graphs for copper oxide and selenium oxide. And as you can see, one can get significant overbindings, whereas the CCECP is within chemical accuracy. Same thing over here. This is shown in the green line. And yet again, the uncorrelated core seems to underbind in the compressed bond lengths. So there's an important point here is that if you do use the uncorrelated core, you can actually get slightly worse results than using an accurate ECP. Some more examples. This is silicon oxide and lithium oxide, and I'm showing these graphs because in some of the cases, the errors are sort of large to our liking, so that we want to improve them further. So in this case, silicon oxide is shown with neon cores, where this is shown in green. And then there's the helium core, which improves the binding energy discrepancy so that it's always within the chemical accuracy. So two of these cores are presented, and it's available. And here in the lithium oxide, similar story here. The darker green line has a slight overbinding, but if you use this so-called regularized CCECP, which actually does not remove any electrons, but it cancels out that divergence near the Coulomb region that we've discussed previously. so that, as you can see, the discrepancy is essentially 0 throughout the whole bond length. Okay, so we talked about the accuracy of coupled cluster, but how does the accuracy transfer to DMC calculations? Well, there has been some tests of the CCECPs, and here I want to show one example. This is desilane, and what you're seeing here is the gaps, the singlet gap, and also the triplet gap using variety of methods. And most important point here is that if you look at this this method, DMC using PBE trial wave function, so essentially a single reference, that gap is essentially very close to experimental values, which is shown here. 2 experimental values are present, and the same thing for triplet gap. So we can see with DMC as well, we can get very accurate results, provided that the ECP is accurate and there's a good trial wave function for that. Here in this slide, I want to show some results which were done, which were carried out by an independent group. So these are some DMC tests for IP and electron affinity for a variety of molecular systems. So these are all the systems that they tested, and this is again done by an independent group. And here, what I'm showing here is the mean energy errors for all of these systems, and they tested on CCECP and BFT pseudopotentials. And they used a variety of trial wave functions, and they used T-moves and also locality approximation. Here, TM is T-moves, and LA is locality approximation. And you can see that there's a consistently the errors of CCECP are smaller than BFT. Although that's a bit small improvement, but it's very consistent. And as you can see, the mean error itself actually goes down as you go to more and more accurate trial wave functions. Okay, so all of these ECPs can be found in pseudopotentiallibrary.org. Currently, the available ECPs go from hydrogen to krypton. For CCECPs, you can find the base sets from double zeta to 6 zeta with augmentations. So essentially, all base sets are there with various code formats, MolPro games, PySCF. And also, as we've said, the UPF files are also there if you want to use them in condensed matter applications, such as in Quantum Espresso. We don't have heavier elements yet, which includes the explicit spin-orbit coupling, but that's work is underway, so that's going to be added soon for some of these elements. And these elements so far, they use this. The type of these elements are AREP, which stands for average relativistic effective potential, so that the spin-orbit coupling is included in an averaged way. So these potentials don't have explicit spin-orbit coupling terms, but one does need to use them for heavier elements. So here, in this figure, the copper element is shown. As you can see, the CCECP is here, trail needs ECPs, ECPs from Jaron et al. is here, which are also quite accurate pseudopotentials. Also, these potentials from trail needs are also accurate from our tests. So those are available here as well. So here I want to show a quick example of using a CCECP in a Scandium atom. First, to do this example, remember that you need to update the workshop example files. So first go to the QMC pack directory and update the QMC pack, and also update QMC workshop. And then you would need to navigate to this directory here, which includes the example for Scandium atom. When you go there, if you look at what's inside, you'll see that there's a geometry file, there's SCF template, workflow file. This is a Nexus file. There's a pseudopotential directory and the runs directory. Essential runs directory is going to keep all the runs. The pseudo directory is going to have the CCECP XML file, which is the QMC pack file. And this download small script is going to download it from pseudopotentiallibrary.org. The geom.xyz is essentially just the geometry of the Scandium atom, which is given here. So if you look at SCF template, you will see that we're going to define the pseudopotential library. We're going to define the pseudopotential type, this is CCECP. define the atom, scandium, define what base set we're going to use. And then these lines are essentially going to download all of these from pseudopotential library. In this case, PySCF uses NWChem, so we need to download the NWChem format. And then later on, there's essentially parsing those files, reading the base set file, ECP file, and then rebuilding the molecule object. So if you remember, this is the scandium atom. It has the configuration of 3D4S2. So in the SCF template, I have defined this irreducible representations in the D2H symmetry. I've put electrons in 3p and 3s, but the 3D it also goes to the AG symmetry, which has the S symmetry and also DZ squared, DX squared minus Y squared type of symmetries. So this is going to be the electron representation for us to get the correct ground state of scandium. In the workflow file, you're going to see this is similar to previous workshops, so I'll go a bit faster. There's a settings portion where you define your machine. And here I'm defining the system. Scandium has 11 valence electrons. The net spin is represented by 2s. So this is not multiplicity. This is multiplicity 2s plus 1. This is just 2s. So in that case, this is 1. In the SCF part, I'm defining a symmetry, D2H. And all these parts are similar to the previous examples. And I have a conversion step, which would generate the QMC pack files. Okay. So if you run this, if you run that section, so the Python workflow, you're going to see that it's going to run the SCF. And once it's run, in the runs folder is going to be an SCF folder with all these files. The scf.py is going to be populated as you would need. Essentially, it populates the geometry, the symmetry, spin, charge, and at the end, it's going to add this conversion step. Okay, so then if you look at the scf.out, you're going to see that it converges in roughly 20 iterations or so, and you're going to see analysis of the SCF. It's going to print out the eigenvalues, and also it's going to print out the population. So you're going to see the 3s and 4s are roughly 2 electrons there, 2 electrons per p electron, and the 3D x squared minus y squared has 1 electron. So it seems we have converged to the correct state. By the way, this analysis is done using this mf.analyze. This is what prints the eigenvalues. Okay, so next, what I'm doing is this step where I'm doing a ground state without Jastro. So this is a VMC run, but which does not include any Jastro term. And also note that here in this example, the number of samples are very small, so that it can be done in the workstation. But in principle, you would have to increase these samples significantly. I've done it in a larger cluster, so these are the results from the cluster. And as you can see, the SCF energy is given here. We've obtained the same SCF energy using a no Jastro. So this is just a quick sanity check for us, so that to check that orbitals are correctly converted. Later on, here I'm defining my optimization procedure. Here I'm defining the number of samples, the minimization method, and then this is the first optimization procedure. The second procedure uses more samples. As you can see, it essentially doubles the number of samples in each increment. And in this case, I'm defining optimization for Jastro 1 and 2 bodies. I'm defining an RCOD because it's an open boundary condition. I have to define what RCOD you want for the Jastro. And here I'm giving these optimization procedures are essentially 5 iterations for each. And so once that is done, you will see that both the energy here and also the variance drop significantly. Note that here the variance, when it starts, it's roughly 3. But if you go back, the no Jastro is roughly 4.5. So even just plain Jastro introduction with zeroed out terms decreases due to the inclusion of electron-electron cusps. Okay. Similarly, I have optimization of Jastro one body, 2 body, and 3 body terms. This is again similar. I'm giving the maximum of 10 iterations, and as you can see, both again the energy and the variance drops a little bit here. And the energy drops significantly here, but variance is very similar to the previous case. Okay, so with that, we've optimized good quality Jastro. Now we would like to run the DMC using DMC on this atom. In particular, here I want to show 3 different kinds. So here on the top, you see that the T moves, I have 3 options, which is no, V0, and V1. Here, no means that don't use T moves, and that defaults to using locality approximation. V0 is the initial work of which was where T moves were introduced. This is the 2006 paper. V1 is the later version of T moves, where it was made sure that the algorithm is size consistent. So basically here I'm finding a dictionary and then looping over these 3 different runs. Then, as you can see, I'm defining the name of the run. Each of these are going to different directories. I'm doing first a quick DMC run, and then here the important step is that the non-local moves is equal to moves, where moves is going to loop over these 3 elements. So if you look at your input, you're going to see non-local moves is equal to either no or V0 or V1. And then at the end, I'm running all of this using my best Jastro term. If you'd like to learn more about this T-move variations, you can go to this link to the manual, where there's a detailed explanation about these algorithms. So once that is done, you're going to see this QMC no, QMC V0, and QMC V1. And if you look at inside, there's going to be these DMC runs. There's a first DMC run, and then these are decreasing time steps. So that is run for each of these directories. And then I'll just here quickly jump to the results. I've plotted all the results here. So what you're seeing here is the fixed node DMC energies versus the time step. The blue line is the locality approximation, and the red line is T-moves, the 2006 version, and the green one is the 2010 version. So as you can see, this is a small system, of course, so that both of these systems nicely converge to the same result, both variations of T-moves. And because locality approximation is not variational, it actually converges to a lower energy. It's also interesting to look at the execution time of these. So I looked at the outputs, and these are the execution times. The locality approximation is of course simpler, so the execution time is small. And as you go to the more sophisticated versions, essentially it gets more expensive. However, because these are, especially the V1 is size consistent, it is recommended to use this version. And as I'll show later, there are other benefits to using that. At this step here, we can compare our results to the exact results. This is from this paper here. For all of these CCECPs, these exact results were published, and the exact is coming from very accurate coupled cluster results, say CCSDT or CCSDTQ with perturbative quadruples. And we have the results from DMC using Hartree-Fock. And as you can see, our results are very close to these benchmark results, and one can get the amount of the fixed node error, which is roughly 37 millihartz in this case, and that's 8% of the correlation energy. So it's good to check the results against the benchmark data. So different, essentially all elements from hydrogen to krypton could be found in this reference here. Okay, so the next thing is the instability, and as I've mentioned, T-moves can actually help with the instability of the QMC runs. And what you're seeing here is the fixed node DMC energy of beryllium dihydrogen molecule, which uses CCECP with 2 core electrons. And in this plot, there's a single reference trial wave function run with and without T-moves, and also a restricted CI trial wave function with and without T-moves. And as you can see, the fixed node DMC energy with respect to the number of steps. So this is essentially could be thought of as the wall time. It essentially shows an unstable behavior, and it doesn't essentially bounce back. Using a trial wave function here with more CI, essentially more determinants, can help it a little bit, but still it essentially diverges. However, in both cases, if you do use T-moves, you get very nice stable runs. So this is another reason for one to use T-moves algorithm in DMC calculations. So the key takeaway here is that the quality of pseudopotentials require thorough testing for using production calculations. As we've discussed, using say a larger core can be good for efficiency purposes. However, you can also buy large errors if you do that. And I want to mention that so far I've only discussed averaged relativistic effective potentials. Calculations with explicit smart terms will be covered in week 8. Here in this directory, all the files will be found in this path. So that being said, that's all I have. And Paul, is there any questions in the chat?
Thanks very much, Gani. Thanks also for going carefully through that workflow, because it's got obviously applications well beyond just testing the atoms that you outlined. So there is one question that I'm going to generalize from a question asked by Juha Tihonen, and that is, what is it about the process of making a CCECP that makes them norm conserving? So how is that enforced or encouraged?
So let me just go back. So essentially, this term is actually included. This is the norm. So if you look at our objective function, essentially this norm conservation term is actually included, and we do in most of the cases we do have this term here, so that it is actually being explicitly matched within some cutoff radius. And this is done due to the fact that if you don't include this at all, what we've seen is that you can actually overfit this quantity in this region. And this was actually shown in some of the graphs, but I didn't talk about them, but I'll show some of these. For example, here in the CCECP.S, the green one, this is only fitting the spectrum and not including, say, eigenvalue properties. And that gives an overbinding ECP, so that we had to explicitly include the norm in the ECP construction. In some of the cases, we included only eigenvalues, for instance, which was related, all of these are single particle quantities, so that just including eigenvalues of these single particle electrons did actually improve the transferability of the ECPs.
Thanks, Gani. A question from Roman Fanta. Is there any reason to use the locality approximation instead of T-moves? So is locality approximation just sort of a historic relic now, and we should always be using T-moves, or are there still reasons to use it?
Yeah, as we've discussed, if you use locality approximation, you have the variance, zero variance property. So if you actually have a really accurate wave function, then you can get very low variances. And from this run, I haven't shown it here for the Scandium runs. Let me just go. What I've seen in this case is that locality approximation has actually slightly lower variance in this case than T-moves. So again, the T-moves does give you an upper bound, but it's not. It doesn't have the zero variance property when you go to the exact trial wave function. So in that sense, there are cases where you can get very close to getting an exact trial wave function. So in those cases, you would obtain essentially zero variance property if you use locality approximation. So I wouldn't say it's a historic thing, but as Dr. Mita suggested, they're essentially complementary to each other, where in some cases it would make sense to use T-moves, saying that in stable runs that I've shown. In other cases, using locality approximation might make sense.
Let me maybe add to that. In many cases, especially when the core is small, so you have something like a semi-core electrons in the valence space, the differences between those two for the energy differences, not for the totals, but for the energy differences, becomes very symbolic. It's simply hidden in the fixed node error. The dominant error in those calculations is actually fixed node. And locality versus T-moves, you might get pretty minor improvement for the energy differences.